Thank you, Professor Lee, for introducing me. So, myself Mohit Mangal. I am from the Hong Kong University of Science and Technology. Today, I am going to present my work on automated optimization of steel reinforcement in RC frames using BIM and hybrid GA. So, there will be three main parts of the presentation. The first part will be the introduction and the background study. The second part will be the proposed BIM-based framework for automated optimization of steel reinforcement. And the final part will be the discussions and conclusions. So I start with the first part, that's introduction and background study. So as we see around, we see a lot of concrete structures, whether it's a home or a building, is mainly made of reinforced concrete. So reinforced concrete is basically an RC frame consisting of RC beams and RC columns. The load incident on the RC frames is transferred to the ground with the help of beams and columns. Now in order to do that, we need to provide steel reinforcement bars in each RC member where concrete cannot take tension. And steel reinforcement bar helps to take that tension and transfer the load to the ground. Now various countries have developed different design codes to calculate the minimum required steel reinforcement depending on the acting design load. Still, we need to decide the number of steel reinforcement bar, the diameter and the layout location of steel reinforcement inside an RC member. Now for a given minimum requirement, there can be a million possible combination of steel reinforcement bars. For example, in the given figure you can see that for the longitudinal tensile reinforcement we can have different number of bars, and for each bar we can vary the diameter also. Even the layout can be varied for an RC member. Hence, it's very difficult to check all the potential solutions before arriving at the best solution. So this problem can be classified as NP-hard problem, which is difficult to solve with conventional approaches, for example brute force method, etc. So in the current AEC industry, we generally use two ways to do the steel reinforcement design. First one is the manual way, where the civil engineer or the structural designer calculates the bending moment and shear force for each RC member, and then calculates the layout like the diameter, the number of bars and the location of bars inside an RC member, which is obviously very time consuming and sometimes leads to mistake. Because every member is unique, you need to do that calculation for each member individually. Semi-automation helps us to make it faster by using some softwares like ETABS or Autodesk RSA, but still it needs human effort to draw the model inside the software application. And we need to provide the settings such as loading conditions, material property, etc. Now no matter which method we use, both the way provide over-design or under-design solution most of the times. So we compared for a longitudinal requirement and we saw that for a requirement of 1200 mm square, the softwares are providing up to 57% over design solutions, whereas manual approach was able to reduce it only till 5%. Sometimes the software does not even provide the minimum required steel reinforcement. Hence, these solutions cannot be used on construction sites. Now let's see what has been achieved to optimize the steel reinforcement in academia. So many researchers have tried to optimize the steel reinforcement for either a component or for the whole RC frame. The idea was to minimize the material cost or even the overall construction cost. No matter which method they used, there were some limitations. For example, they never considered the combination of steel reinforcement bar with different diameters, and sometimes the solution obtained from these methodology does not satisfy the design code constraints. Hence, you cannot use it on construction site. Moreover, steel reinforcement design process itself was not fully automated. There were some manual inputs. For example, if we have an architectural model, we have to create a structural model, do the load calculations, then provide steel reinforcement, create the steel rebar model in 3D, which takes a lot of manual inputs such as material information, loading conditions. Now the problem, if you change the architectural model, you have to repeat the whole process again, which adds up to a lot of redundant work. Moreover, no 3D visualization automation was considered till now in the steel reinforcement design process. Hence, we can say that for the steel reinforcement design, we have some limitations, like there are too many manual inputs, there were partial optimization, and there were no 3D visualization. Hence, we can say there is a need for an automated steel reinforcement design framework which provides optimized steel reinforcement design and also supports 3D visualization. Now, BIM can help us. BIM supports automation, BIM also supports 3D visualization, and BIM can support optimization. So let's start first with what is BIM. So BIM is basically a digital representation of a structure or a facility. For example, in a given figure, we have an RC beam showing the 3D view of the beam. Moreover, it contains the geometric information like the width and the depth of the RC beam. And it also contains the semantic information like loading information and support information. Taken together, these all information are required for steel reinforcement design. Hence, it can help us to automate the steel reinforcement design process. Moreover, BIM can be linked with other applications like structure analysis, etc. Together taken, they can automate the steel reinforcement design process. Moreover, if we connect it with some optimization methodology or engine, it can automate as well as optimize the provided steel reinforcement design, giving us the final model in 3D, which can also help us to automate the construction drawing detailing. So we can say that our objective will be to develop a BIM-based framework for steel reinforcement design, which will not rely on manual inputs, which will also consider the limitations of past study, like consider different diameter combinations, and which will also support 3D visualization. So BIM model will provide the geometric information, loading condition and support information. It will further link with structure analysis application to provide the bending moment and shear force diagram. Taken together, they will help us to automate the calculation of number of steel reinforcement bars, diameter of steel reinforcement bars, and layout for steel reinforcement bars. So now let's discuss the second part of the presentation, that is the proposed BIM-based framework for automated steel reinforcement design of RC frames. So our framework has 4 modules. The first one is BIM Model Extraction. The second one will be the structure analysis. The third one will be the steel reinforcement calculation according to design code. And the fourth one will be the steel reinforcement optimization, satisfying the design code requirements. So I start with the first one, that is BIM Model Extraction. So in order to use BIM for steel reinforcement design, the BIM model should contain all the information. For example, the geometric condition, the loading condition, as well as the end support conditions. Once we have a BIM model containing all the information, we need to extract that information for further structural analysis. That's where second module comes in. So once we have the extracted semantic and geometric information, we will import that information into structural analysis application to calculate the bending moment as well as the shear force value for each of the RC element in an RC frame. Till now the process is pretty straightforward and need no explanation. So let's start with the third module, that is the steel reinforcement calculation. Now before we go into steel reinforcement calculation, we need to find out what type of calculation steel reinforcement are we dealing with. So in a typical RC member, we have 3 types of reinforcement. First one is tensile longitudinal reinforcement, which is in the bottom part of an RC beam. Second one is compressive longitudinal steel reinforcement, which is at the top part of the RC beam. And the shear steel reinforcement links, which are the vertical links provided to counteract the shear force acting on an RC member. Now various codes have been developed for different countries. In this work, we will use British standard, which is used for Hong Kong. So now I will start in detail the calculation of steel reinforcement for RC beams. So the first one will be the tensile steel reinforcement, which is the total cross-sectional area of longitudinal bars provided in an RC beam, which can be formulated in a given equation like given in the slide. Now we can see there are 2 types of variables. First one is the number of reinforcement bars, and second one is the diameter of each reinforcement bar. Hence we have a total of nt plus 1 variable, 1 for number, and once we have that number, we have to calculate the diameter for each reinforcement bar. Similar calculations can be done for compressive reinforcement, and we will have nc plus 1 variable. The last steel reinforcement will be the shear reinforcement. Now as we know that shear reinforcement is not, acting shear force is not constant over the whole length of RC member. Hence the shear reinforcement will vary along the length. So first we will divide the member into different sections having constant type of shear reinforcement. Once we have that subsections, we will try to find out the spacing between 2 vertical shear stirrups. The third part will be to find out the number of shear links in each stirrup. For example, in the given figure, we have 3 number of shear links. The fourth variable will be the diameter of vertical shear links. So in taking together, we have 4 variables for each subsection. Now in a general RC beam, we have at least 3 subsections. So we are dealing with 12 variables. Taken together with tensile and compressive reinforcement, we are dealing with at least nt plus nc plus 14 variables. Similar calculations were also done for RC columns, and we can say that our objective function will include the total beam reinforcement area as well as the total column reinforcement area. Now reinforcement is not only a matter of optimization, it should be easy to place on sites. So we look into what's the problem faced by contractors during the placement of steel reinforcement bars. And we found out 3 types of problems. First one is the number of steel reinforcement bars. So if you increase the number of steel reinforcement bars, it is so congested that concrete cannot flow through it. It will affect the final strength of the RC member. Moreover, if you have a higher diameter of steel reinforcement bar in your design, you need big machines to bend them in required shapes and angles. The third one will be the combination of steel reinforcement bar of different diameters. If you have a detailing having different types of bars, like 10 different types of bars, workers can make mistake while placing them on site. Hence, there can be, and that will finally affect the overall strength of the RC member. Hence, we develop the penalty functions to restrain the number as well as maximum diameter of steel reinforcement bar. For the third problem, we limited our methodology to consider at most 3 different types of steel reinforcement bars for a given RC member. So we can say that our revised objective function will include the total beam reinforcement bar area, the total column reinforcement bar area, as well as the penalty functions. Now once we calculate the minimum required steel reinforcement for an RC member, we need to do the optimization part, that is to provide the steel reinforcement satisfying the minimum requirement. Now we have an objective function to minimize the total frame reinforcement area that will have various design code constraints like loading and end support constraints, serviceability constraints, and material strength constraints. And it's impossible to check all the solutions to arrive at the best solution. Hence the problem is NP hard. Now to deal with this class of problems, we have several heuristic approaches developed in the past like particle swarm optimization, ant colony optimization, and genetic algorithms. In the current work, we use genetic algorithm to tackle the problem. So genetic algorithm is a process of doing the natural selection by crossover and mutation in order to find out better offspring from the existing parents by the way of using crossover and mutation, which help us to incorporate randomness to search new solution space. GA also help us to handle constraint problem, which is the current problem. Like our current optimization problem also have constraints. Now in order to improve the genetic algorithm solutions, we incorporated another approach, that is hook and give approach. So this will help us to look for the solution in the local vicinity of the solutions obtained from genetic algorithms. So in this one, the process started by getting a solution from GA, then the variable is changed one by one to find out the better solution in the local vicinity until and unless the solution converge. So this is the overall optimization approach. So first one, we will create first generation randomly, then we'll apply the hook and give approach to find out the 2 best solution in that developed population. Once we have that, we will apply crossover and mutation to get the better offsprings from the existing parents, and taken together, the overall process will be called a hybrid GA-HJ approach. Now this process will run generation through generation until unless we meet the termination criteria. Once we have the termination criteria, the best solution of the last generation will be the optimum solution for that given problem. Now in order to decide the termination criteria, we decided 2 conditions. First one is the necessary condition, that is the result obtained should be within the desired threshold. And the second one will be the sufficient condition, that is once we have the result within desired threshold and we don't see any improvement in successive generations, we will terminate our generation process and will find the best solution as shown in the graph. Now, till now we are doing optimization. The final results are in text format, and it's very difficult for contractors to understand that text format. Hence, we need to do something to convert those text results into 3D view. That's where IFC model comes in. So IFC model help us to represent BIM model into text. So with the help of IFC, we can reverse the process. So we will develop the IFC model of the given RC frame or RC member. Then we will incorporate the optimized steel reinforcement detailing solutions, and we will update the IFC model. Once we have the modified model having all the steel reinforcement details, you can use any BIM application to show the 3D visualization. So we can see that the final result will contain steel reinforcement inside an RC member. Moreover, it will also help us to automate the construction drawing detailing, like we can create the drawing automatically for a given RC frame. Now this is the overall framework. Now we will try to validate the framework on a given RC member. So we consider an RC beam having geometric condition and loading condition as shown in the slide. Autodesk Revit model will be used as BIM model, and Autodesk robot structural analysis will help us to do the structural analysis of the given RC frame. We also developed a optimization engine based on developed hybrid GA-HJ optimization approach. So this is the overall framework we implemented on the given RC beam, and this is the solutions we obtained from the optimization after the optimization. So we can see that for a given requirement of 3195, the existing software are giving up to 96% over design, whereas our solution is giving over design only of 0.004%. Hence, our developed methodology provides better solution compared to existing approaches. Moreover, our developed algorithm is pretty fast. It took only 10 milliseconds to deal with first two cases to find out the best solution, and only 72 milliseconds to find out the best solution for last loading conditions. Penalty functions also help us to reduce the number of bars, types of bars, and the maximum diameter of bars without affecting the final solution that much. So this is the overall solution for the given RC beam. We can see that for the given RC beam, software sometimes provides solution less than the minimum requirement, whereas the developed methodology provided solution always satisfying the requirement and better than the existing approach. So I'll show the final framework, the developed plugin based on final framework. So this is the considered RC frame. We can click the button developed by us, and this will help us to show the information. Then it will transfer the model for structure analysis and optimization. So this is the optimization carried out and the results are obtained. The IFC model is modified at the back end, and we can open the modified IFC model having the steel reinforcement bar inside them. So this is the final solution showing a 3D visualization of steel reinforcement. So let's go to the final part, that's discussion and conclusion. So in this work we developed a BIM-based framework to optimize the steel reinforcement for RC frames. The framework automates the overall steel reinforcement design process. It also addresses the limitations of past research to yield better solutions, and it also considers 3D visualization for better understanding. Still, this work has some limitation, that is, it was only developed for RC beams and RC columns, and it was not tested for non-rectangular RC components. So we will try to address other RC components in future, and we will also try to extend our framework to account for non-rectangular RC components. Thank you. If you have any questions, please.
We have the third presenter coming to us, Rashidi.